Hello and welcome everybody, and thank you for joining to episode number 14 of Going Meta. Hey Jesus, how are you doing?
I'm great, Alex. Great to be here. It's
Great.
fantastic to be on our episode 14 with a
Yeah,
super interesting topic.
yeah, great to have you. I was when I wrote the topic, I had to pay attention that I didn't write taxidermy reconciliation because
Oh, there might be a bit of that.
maybe a little away from the usual, but that could have been interesting as well. But maybe let's stick to to what we do.
Yeah.
The taxonomy reconciliation is the actual topic. So I'm looking forward to that. I'm interested to know or to learn what that is exactly, and what we're going to do today. Before that, before we dive in, I'd like to say a few words about a few things that are happening here, and I'd like to make you aware of those. So this is the Neo4j training series is the number one topic I'd like to mention is from next week onwards. 15th of March, be hosting a couple of free online workshops you can join. They will be, as I said, online, so no worries if you wherever you are, you can connect. They are about the intro to Neo4j that Michael is doing next week. Then we do intermediate cipher with Adam. That's a little bit more advanced for beginners as well as for people who know a little bit about cipher and want to know more. On the 29th, Will does how to build a routing application, so with geospatial data. So I think that's pretty cool and interesting. And then we do a short break because it's Easter holidays in many countries. But on the 12th of April, we're back with Spring Data Neo4j overview that Garrett is doing. So Garrett is one of the developers and drivers for the Spring Data integration, and he will show us what is Spring Data, what can you do with it, how do you create your apps, how do you build your apps using Spring, and all of that. So it should be interesting, and also it's a bit more advanced. But if you're interested in any of these topics, please register. The link is in chat. Link is here on the slide. So would be great to have as many people as possible. To have your questions, to get to learn a little bit more on Neo4j as we go. And this is the one thing I wanted to mention. The other thing I wanted to mention is it's International Women's Day tomorrow, 8th of March, and my colleague Yolande is hosting a panel of a couple of Neo4j colleagues who talk about how it is for women in tech to work there, to work with in this industry in a predominantly
In
male
this white male industry, right?
exactly yes, yeah. So to see what the challenges are, but what's the motivation as well, and have to have any low points, but obviously hopefully also high points in their career, and maybe some tips and tricks how it is for people who join a fresh start into this career, or maybe who are there already for a while. So that's tomorrow evening Central European time, or morning Pacific time. So it should be available for most of you. So I'll watch this. I hope you do too. And it's a great topic and an interesting conversation.
Absolutely. I encourage you all to join that one.
Yeah, that's what I had in terms of announcements. But then, I think we can dive into going meta, taxonomy reconciliation.
Perfect. That's great. Thank you very much, Alex. So I'm going to do as usual a very brief introduction to the topic, and then jump straight into our usual friends, which is the Bloom, the browser, the hands-on part, of course. So let me share my screen and share the screen. Let me know when you can see it. Should be an empty desktop. Probably you can see my deck.
Here it is.
Good. So first of all, let's start by describing what we mean by taxonomy reconciliation, and maybe it's it's a topic that we've at least we've mentioned taxonomies, we've mentioned ontologies before. Let's go into probably a slideshow to make it a bit more better readable. But a taxonomy is a way of capturing knowledge, right, and organizing knowledge, and it's a way of classifying a domain, classifying the world. And you probably have heard us, me in particular, describe a knowledge graph as a combination of facts about the world plus explicit knowledge, right? Something that helps us make sense of this data, and to eventually derive more information than the one that's explicitly stated. And we use that, you probably remember, Alex, in I believe it was episode 2 when we talked about semantic search, right? So you probably remember how we load some articles, we extracted some entities, and we overlaid these. Again, it was an ontology, but in the end, the taxonomy is probably a type of ontology that just includes the hierarchical part of it. So it's just a classification, an organization, hierarchical organization of categories, right? So we all know taxonomies, we all know classifications, right? That's how we classify, what with the right term, like living creatures, right? In this kind of way of organizing them in a family tree, and what I mean is that this is explicit knowledge, because we know that we can use the information in that taxonomy, in that classification, for example, to derive the fact that a turtle is probably, or a lizard, it's more an obvious one, is closer to a snake than it is to a spider, right, or to a crustacean, to a crab, right? Yeah. So there is some knowledge, and that's purely a graph statement, right? It can be described in terms of distance, right? So actually there are metrics, there are semantic similarity metrics. I don't know if we've talked about these in previous episodes. I don't think so. But they are defined to compute the similarity between two topics or two elements in a taxonomy, in a tree, based on a number of elements. The simplest one is purely path distance, right? So the further away you are, the more different you are, and the closer you are, the more similar, which is exactly what we just said. So it is a data structure that actually captures the knowledge and that we can use. And there's many variants to these semantic similarity metrics, right? So you can take into account the depth, right? A similarity that takes place high up, right? So maybe I'm not a scientist, but a similarity that happens towards the root of the tree is too broad, right? So maybe let's be silly, but animals and plants at the root, they might be close, but as you dive into the tree, you see all the variants. So you might say, hey, an animal is very close to a plant, therefore they're very similar. Yeah, but then you can take into account depth, for example, and that's where more sophisticated metrics like this Likert-Chodorow takes into account, or Wood-Palmer. But again, I won't go into that today because that's not the topic, that's not the subject. It's just to insist on the importance of taxonomies and how, I love taxonomies. I think, we like classifying things, and they're very, very useful. I mean, in that case, we used it to recommend which articles should you read based on what you're reading at the moment. But ultimately, what we were doing is traversing the taxonomy. So they're very, very powerful and useful structures. So what we're doing today is what happens when we have multiple taxonomies eventually developed by different parties that are not perfectly aligned. So they see the world, partially in the same way, but not exactly in the same way. So it, in a way, can be seen as a data quality, knowledge quality exercise. So how do we detect these misalignments and how we work with them? So does that make sense?
Mm-hmm.
Perfect. So in order to do that, we're going to use 3 public sources that we might have worked with before. At least I'm sure Wikidata is one that we constantly use. But we wanted to take three taxonomies, right? And I'm going to use 3 infectious disease taxonomies. Why not, right? So that was what that came to mind, and I picked these 3 sources because they're pretty popular, they're well maintained, they're rich enough, and they're reasonably similar but not identical. So one is the medical subject heading, sorry. The other one is the disease ontology, and the other one is Wikidata. So all 3 of them are made available in RDF. So we're going to be using new semantics as always to input that data. We'll prepare, we'll go through the ingestion phase, and then we're going to try and do things like what you see visually here. So we have let's say a portion of the taxonomy in each of the 3 sources, and there will be cross references across them because that's something that's available for us. So we'll see how Wikidata and Nash and some others actually provide some cross references. But again, this is not complete. This is not exhaustive. So we'll find cases where it's perfect, where things align, forming it's kind of a flat, but it kind of a triangle in the case of 3. So this is the same as this, is the same as this, and is the same as this. So it's perfect alignment between the 3 of them. But there might be cases where the triangle is broken, or where there's just a portion of it, or where there's even more complicated patterns. Because it's all about patterns, all about shapes in the graph. So that's exactly the kind of thing that we're going to be analyzing. So I'll pause here with the slides and jump into the sandbox to first build these 3 taxonomies, these 3 trees in the Neo4j instance, and then we'll get back here to look at specific misalignment patterns. Good?
Yep.
Perfect. So while you were doing the introduction, I started my sandbox. So I have just a recently created one, so all empty. And here's where I'm going to be working. And like I said before, 3 sources. The first one is Wikidata. Why not? And without going into all the details, I'm going to do the usual. You know that Wikidata is a large, I think community curated data set that we can interact with in a number of ways, but the one that we prefer is through this Sparkle interface. So I'm going to copy one query, probably go just high level into the details of what we're doing, and just expect you to believe me. All these will be shared in GitHub as usual. But basically, what we're doing here, and let's forget the construct part. I'll get back to these in a minute. But basically, we're selecting things in Wikidata that are infectious diseases. That's what I said. So that's kind of the root of my taxonomy. And I'm going to navigate the taxonomy following the subclass of and the instance of, right? These are the 2 types of, it's not a super strict taxonomy, so it uses a number of predicates, but these are the ones that work in this case. So I'm looking for things that directly or indirectly are subcategories of these infectious disease. And that's what this asterisk in Sparkle represents. And I'm going to get for each one of them a label, a descriptor of it, in particular the one in English, because it's a multilingual data source. I just want the English version of it. Mm-hmm. And then I mentioned before that I'm going to be getting some of the cross-references that exist. So in Wikidata, we have this P486, which is a mesh descriptor. So if you remember from my slide before, we're building this taxonomy, but we have references to this mesh taxonomy as well. So that's what this predicate is going to give me. So I'm doing a bit of hacking here, producing the URI. And the same.
You looked for this beforehand, or how do we know?
Yeah, well, that's
the mesh.
a very good point. Well, these are very popular data sources, right? Mm-hmm. So these are in the life sciences domain. So this is a data set that we worked with in the past. I'm going to copy the same interface for the mesh data set. So these are, I don't know if, oops, went to the wrong one. Is this the one? Oh, so there's a Sparkle query editor. That's where I wanted to go. Sorry. So I don't know if you meant if I knew up front Wikidata, Mesh, and the disease ontology, or whether I kind of knew my way into Wikidata and how did I know these 486, 699, and things like that.
Yeah, how did you know 486 and 699? Yeah.
Good. That's a good question. So let me show you how did I know that. So if I let's run this first part of the query, for example, if I return one single e, select star, that's going to return me some instances, and if I click on them, this is going to take me to the Wikidata page. So congenital toxoplasmosis, right? There you go. One fantastic infectious disease. So this is the more kind of human readable page, right?
Yeah.
This is all stored as triples, but what you can do is explore it visually here. So you can say, what do we know? I mean, first of all, is the instance of subclass of that I mentioned before. So this is the two relationships that I'm going to navigate to build the classification, the taxonomy. But I see that there's some additional information here. So we have health speciality and so on and so forth. And we find here that there are some additional identifiers. So I found, hey, there's a mesh descriptor. That's cool. That's exactly what I want, because that cross-references to the other data source. So if you pass the mouse over, you see down there, is it readable? You see that tiny 486? Well, now it popped there.
Yeah, now I see it. Yep. Mm-hmm.
So there you go. So it's I don't know if there's a catalog, because it's such a huge knowledge graph that I cannot claim to be an expert on every single. So what I do typically is that I go to the human readable one, and I select the bits that I find relevant, right? So in this case, the mesh descriptor. There's also the disease ontology, as you can see, property P699. And then like Medline, that would be another one, which I'm not using in this context, but there's a number of predicates that I would take from here and translate into actual Sparkle statements. So
okay,
that's the idea. So what I'm doing then is, like I said, basically getting a collection of things defined as categories in Wikidata that kind of are children, direct or indirectly, from infectious disease. And for each one of them, I get their parent and the cross references to the mesh taxonomy and to the disease ontology. So that's what this query returns. In Sparkle, again, without going into too much detail, I can run a select query like the one I run that returns a tabular structure, or I can build a construct query that returns actual RDF, and I'm going to use that to then stream it directly into my Neo4j sandbox and import it. And effectively, what I'm doing is I'm saying for each disease that I find, I'm labeling it as WD disease, as Wikidata disease. I'm getting the label, the parent, and the two references, the URI of the mesh ontology, mesh taxonomy, and the disease ontology. And I link them together with this same as relationship. Right? So this produces RDF, right? If I run it, we can see how it streams some triples. And there you go. So subject, predicate, object, as usual. And what I'm going to do is, okay, well, that's exactly what I need. And I'm going to go to my Neo4j instance, to my sandbox. And before I start importing any RDF, as you know from many previous episodes, we have to create a constraint. And we have to provide the configuration. Right? So in this case, I'm doing something slightly unusual, and I'm using, normally I use ignore. Map is just the variant of ignore that gives me the option of defining mappings. So sometimes I will want to rename things. We'll see that later on when we import the disease ontology. But for now, let's take it as if I was using the ignore option. So that's the configuration. And now I'm in a position to actually run the input and see what that looks like in Neo. So as usual, I'm going to copy paste, but nothing new here. What you see here is exactly the Sparkle that I just run on the Wikidata side, right? So this query, I've pasted it here. And I'm storing it in variable query. And all I'm saying is calling Neo semantics and say, go and import all the RDF that will come out of running this query in this endpoint, which is the query Wikidata Sparkle endpoint, which is not other than this one here. So I'm basically doing programmatically what I was doing manually. And these will return some triples, and I will just ingest them. So if I run that, hopefully that's going to be reasonably quick. It's just a few thousand triples. There you go. It's over the internet, of course, so it's actually sending the request from my sandbox all the way to the Wikidata server. But we've ingested 2,700 triples, and it all looks nice. So what we can see now is that we have, as expected, diseases, nodes labeled as diseases, organized in a has parent type of taxonomy. There we go. So I just click there, and you can see how my nice nodes are organized in a not exactly a taxonomy, right? So you see things that are a bit, well, no, I wasn't going to say unexpected. We knew that that was going to happen. But what does that mean? Well, first of all, we can see that it's all traceable. So we have nodes that represent the Wikidata diseases. We have the label, as expected, central nervous system viral disease. And we have a reference, the unique identifier, which is the Wikidata URI that I can click at any time. And that would take me, as before, to the page that describes the entity in question. Right, so that's all good. Now, the thing is, that doesn't look like a nice taxonomy. A taxonomy should be a tree, or most of the time should be a tree, at least a graph. But I wouldn't like to find, well, these are not necessarily loops, but it's kind of there's an element of redundancy there, right? Because if we, this is the has parent relationship, let me make it a bit bigger. Is it readable, Alex, or should I make it a bit bigger?
Well, I think it's readable, but maybe if you, yeah.
There you go. Let's see. The problem is then when we put a lot of text, it's going to be trickier. But anyway, things like that are not wrong, but they're not necessary. So I'm saying that this disease has these as a parent, which has these as a parent. And, this is kind of a redundant link, right? This has these other as a parent, more as a grandparent, if you want. But it's something that I don't really need in my, it's kind of, it definitely is in Wikidata, and I've just imported the way it was. But I can say these are redundant links, and we don't really need them in the graph. So we could perfectly remove those shortcuts, as I call them, and that these are easy to detect, right? Because I can write this Cypher query that says, okay, we have a Wikidata disease that's connected to a child in two ways. Notice that this, let's call it, instead of the Wikidata disease, to make it more readable. So we see that this is the same thing, the same Wikidata disease, that's connected to a child through two different paths. One is direct, one hop, and one is multiple hops, more than one, two or more. So this is this pattern. I mean, it can be two, it can be three, it can be definitely more than one. But basically what that says is that this guy here, this is a shortcut, and I could live without it, because if there is a path, I don't need this shortcut. So I could say go and well, I could return a couple of them. That's just to check that the query works, and we see that this does return effectively these type of scenarios. So we have, well, let's put it nicely like that. So it would be something like that, right? So we see that we have a shortcut here and a shortcut here that we could live without. So I just take that query, and I could say, well, you can go, and every time you find this pattern, go delete the shortcut. And that's just a way of cleaning my tree. It's just 44 relationships that I don't need, and that's going to be neater in this case. But anyway, that's kind of a data quality thing. But what we have at the moment is something like this. We saw briefly, but I can run a query. For example, I'm looking for one particular disease, anaerobic cellulitis, and I can find for it the path that takes me all the way to the root of the taxonomy, to the root of the tree. Mm-hmm. And I know I specify that it's the root of the tree because it doesn't have a parent. That's my way of saying in Cypher that I'm looking for the whole path from that disease all the way up to the root. And if I run this query, I get a nice, I was going to say a tree. It's not necessarily a tree, and it's a bit too big, but let's make it a bit smaller. So, and let's make it look like a, okay, let's keep in mind the arrow direction. So maybe something like that would be the right thing. So it's not look like in the, I mean, it's not like there's not the notion of a shortcut like in the previous case. These are genuinely two paths, two possible classifications. So that's what I meant. It's not always a tree. It's ideal when it's a tree. It makes certain types of processing easier, but it's not always a tree. So in this case, we have, well, there you go. That's the tree for this anaerobic cellulitis. And we can see how we have two roots in a way. So it's, I don't know, we can make it probably more readable, but making them a bit bigger, it will contain more of the text. But there you go. So we have the Wikidata taxonomy, and I was thinking that this query, it's a good one to create a Bloom perspective, right? So I have Bloom here, and I'm going to create a perspective. So not a perspective. I was going to say a search phrase. So
okay.
Let's create a perspective and let's use it. Perfect. So I can, of course, find diseases, but what I wanted to do is maybe create a search sentence. So say cipher search phrase based on that query, except that now I'm going to kind of parameterize the query, the search term. So that's my query, the one that I was using before. I want it to work in the general case, not just for this cellulitis one. So I'll say I'll pass a disease name. And my question is taxonomy 4, and I will pass the disease name. There we go. So that's it. I think that needs some. So that's my my search sentence, and I want to get suggestions based on a label key pair, and I want to get the diseases, and I want to get the labels.
Yep.
So if I say that, I'm now going to be able to say, okay, show me the taxonomy for, it was anaerobic cellulitis, right? So there you go. So I can do the same without having to write the cipher. If you are a non-technical user, sorry, I'm making a bit, I might need to zoom out here a bit, but I can maybe make it fit there. And maybe in this case, I can use a hierarchical layout that will look more, and I believe I can I revert it? How does it? I can't remember how to, oh yeah, here we go. Bottom to top, that looks more like a hierarchy. And here we go. So that's pretty much what we were getting before, right? So in a nicer way. But so that's an easy way to, without having to write the code for us to explore a single taxonomy. So that's the first step, right? So we have the first of the 3 taxonomies that we want to import. Good. So we're going to do the second one, and I'm going to go a bit quicker, but essentially it's exactly the same process. So we have a Sparkle endpoint for the medical subject headings, which is, again, a taxonomy maintained by the National Library of Medicine. And without going into all the details, I'll do exactly the same thing. Let me copy my cipher fragment, go to my sandbox, and you will immediately see that it's exactly the same. So we have a query, slightly different to the other one, but that produces this very similar graph, except that now I labeled it as mesh disease instead of Wikidata disease. I want to tag them to be able to determine where do they come from, but I keep the label and I keep the parent taxonomy. So who's the parent reference. I send the request to the relevant endpoint, not the Wikidata Sparkle endpoint, but to the mesh endpoint. And if I run that, that will bring another set of triples, a few thousand. There you go, 3,000, this time from the other taxonomy. And just like we did before, I'm going to clean the shortcuts. The only thing that changes here is I'm doing it for the mesh disease, so nothing new here. That will remove a bunch of 15 only. That's not too much. And we should have now a 2 taxonomies that should hopefully be linked. Oh, one thing that I didn't pay attention to before, but that was there. Remember that when I imported the Wikidata one, the Wikidata disease taxonomy, one of the things that I brought with me was the same as relationship. And that was something that I was creating to link the cross-referenced sources. So if I click on same as, we'll find that there are, let's make that bigger. So we will find my Wikidata entities. Let's make that a bit bigger here. That are linked to something. In this case, this is still like I would call it a container, like a stub. It's still empty. We know that it points is the same as something, but this is from the disease ontology, which we still haven't imported. So we'll come back later. But we already have some matches. That's another one.
Okay. Yeah.
Sudoku. It sounds like Sudoku, but it's Sodoku. I didn't know that was an infectious disease. Anyway, there you go. So we have
can be if you play too much.
Yeah, there you go. So I'm not going to click because you know how these things, maybe we
know what it is. Yeah.
But you see, this is a Wikidata disease that came with 2 cross references, one towards a disease ontology ID and one towards a mesh. And then when we load the mesh data by magic, the thing got by magic. We know that it's not by magic. We know that near semantics, when you import RDF and 2 things use the same URI, it magically, I've said it again, it's not magic, but it merges it into the same node, right? So later on, we will stop finding these kind of purple unidentified URI. At the moment, all I have is the URI. But then when I bring all the details about this thing and I load the disease ontology, it will become fully populated with the rest of the attributes. That has already happened with the mesh disease, and we start having already alignment between the 2. So we have our Wikidata disease taxonomy align with the mesh disease taxonomy. Now the thing is,
and I missed this. You did load the URIs already when we did load the Wikidata.
Correct. So if we go back here, remember that here we go. So this query would produce this type of URIs. So it produces the same as, and it gives me the URI of the disease ontology and the URI of the mesh reference.
Yeah.
So all it contains is kind of the key, the unique identifier, which is the URI. Yeah. And in the first instance, we didn't check, but it was something like that. It was just a resource with the URI.
Yeah.
Right. But then when we brought the mesh, then the 2 things blended together into a complete node. And we'll see that it's enriched with some taxonomy, of course, like we would expect on both sides, right? So we have these first 2 taxonomies already aligned. Mm-hmm. And one thing we can do is do a side-by-side exploration. And I'm going to take the example before, the anaerobic cellulitis that we used in the previous example. And I am going to navigate it a bit more, right? So let me paste the query and interpret it rather than trying to type it. But you remember what we were doing before, right? So if I break the query here, we were looking for a disease by name. We could do it by URI, by whatever. And I want to extract the whole tree, the whole taxonomy, all the way to the root. That's the query that we used before. So that would give me, for the anaerobic cellulitis, the whole path all the way to the root, which might be, branched like we saw in the previous case. Now what I'm doing is I'm putting this path, this kind of, path in the graph in a variable that I call taxonomy. Right? That's the taxonomy for these anaerobic cellulitis. Mm-hmm. And what I do is for each one of the nodes along that path, for each of the categories, for each of the taxons in the taxonomy, what I'm going to do, that's what I'm doing here, iterate over the nodes in that path. That's what unwind does in Cypher. What I'm going to do is run a query, and I'm going to say, for each of the nodes in that path, find if there is a same as that connects it to a mesh disease. it won't be there always. That's why I use this 0 or 1. It may or may not be there, right?
Yeah.
But if it's there, I want it. So I want to see how this category, this taxon in the Wikidata taxonomy links to a mesh disease. And then I want also the taxonomy, the parent relationship on the mesh side. So it's kind of a long path, but what I'm saying is, okay, jump to the twin node on the other side and give me the taxonomy that takes me all the way to the mesh root, which is exactly the same logic as we did before. Something is the root if it doesn't have any parent. So I return all these results, and that will give me a rich thing that I'm going to have to lay out in a, let's first recolor things a little bit, because I'm not liking these very much. Let's put it a nice coloring. So now we have the blue ones are the mesh elements, and the orange ones are the Wikidata. Now we have same as that bridge the two. Let's mark them in red and make them a bit thicker so we can see them. So let's do that. Let's put them. What's a good layout for these? This is all about, playing around. Does that make sense, or should there be? This should be more here. So this is actually at the bottom. Sorry about that. That's trickier than it seems. It's like
it's like one of these games.
Exactly. So yeah, that should look is a bit like what we saw. No, that's has parent. So still another one here. Oh. Sorry, that's let's make these a bit bigger. Infections that has parent. I want arrows up all the way. Is that it? There we go. So that's the one. That's the one. So let's make horizontal the ones in same as.
Yeah.
Okay. So bacterial. This looks like there's more than I was expecting, and it might be a bit more complex to interpret. But let's try to make sense of these. So this is okay. This is because the arrows point up. This is going to be under here. Anaerobic cellulitis. Okay, so the first thing is, well, there's no equivalent for the anaerobic cellulitis, which is fine. But we see that there is and let's make that a bit, let's do the has parent a bit thicker as well to make it, to try and identify shapes. So there's a link between, first of all, I think it's a pretty complex to make sense of in a single go. That's where we're going to break it down into more consumable chunks. But the first thing that we see is that there's an alignment between these two at two levels, right? So there's an alignment between these cellulitis and bacterial diseases. And again, let's make them all a bit bigger so that the text is more readable. But we're lacking this has parent that exists on the Wikidata side, but not on the mesh side. Right?
Yeah.
So we see that these two things, in theory, well, they should be. I mean, maybe there's a potential has-parent relationship that we're missing on this side, right?
Yeah.
Then there's another case here where we see, in this case, maybe we want to bring this one out because this is probably a bit noisy, but we see that these two are well aligned, right? So maybe, hang on, let me remove that one because this is being a bit noisy here. Oh, no, I don't want to do that. Sorry, I'm going crazy with that's it. And you go away. Okay, so I was going to say that we see this kind of V shape here. So we have this skin diseases bacterial. They're perfectly well aligned. So this skin infection, I mean, with a different name, but we have this kind of V on both sides, right? So we see, and they're perfectly aligned. Anyway, so this is more of a visual exercise, and can be a waste of. I mean, in some cases, I mean, if you're an expert, maybe the names mean something to you, or you can determine, that the fact that some of them might be spelling differently, but they're effectively the same. that can be useful. But this is a tedious exercise, right? So what you want to do, and that's what we're going to be doing, is try to detect those patterns and surface them by using Cypher. So this is just a way of showing how, even though there's alignment at different levels, there's significant differences in the two taxonomies, right? So let's complete the picture by loading the third one, because this is going to be slightly different. And up till here, we've seen that the both Mesh and the Wikidata taxonomies offer the Sparkle endpoint. That's very powerful because you can take full control of what you do and what you extract and how you ingest it into Neo. But sometimes that's not the case. And that's exactly what happens with the disease ontology. The disease ontology is published as a I actually can probably quickly query disease ontology. It's published as a file, right? This is there you go. So, well, this is probably a more human explorable one, but you can export it as a file, so you can download it. But there's no you have the different releases, and probably we'll get the latest one. But it's a file. I mean, there's no query interface that I can use. That's why I'm going to have to do a bit more sophisticated processing on the neo-semantics side. So here's what I'm going to do. So one of the things that we can do in neo-semantics is we can read from an endpoint and without importing. So this is reading from this endpoint, which is where the disease ontology lives. And it's streaming out, I'm going to put a limit of 100, streaming out the triples. Of course, you want to not make mistakes. Yield, call. Yeah, you need a return, obviously. So have a return star. And you have the subject predicate object now. It might be messing them around and shuffling the order. And that's, I mean, the performance of the endpoint might vary, and in this case, the OBO library endpoint might be a bit slower than we thought. But anyway, so you have, because I use star and without the order is putting it object, predicate, subject. But anyway, we have the triples there. And the thing is, I cannot query it, but I can apply some filters here in neo-semantics because I get the triples. I can say, okay, there's loads of information here that I probably don't care about, information about the ontology, some predicates that are not very useful. All I want is for all the categories defined, I want the label and I want the cross-reference if that exists. That's all, and the taxonomy, of course. So I can filter these predicates with an expression. I'm going to show it as usual, and then explain the query. It becomes a bit heavier on the neo-semantic side, but let's step by step to see what happens. So what we saw is that this will go and read the ontology and stream the triples. I mean, I'm setting normally you can set the limit on the number of triples that you read, but I want to read them all. Like this, I set a very high number, and like this, I get the whole ontology. So I'm streaming out the subject, predicate, object, all the triples that are in this file. And I want to extract from all the elements defined in this ontology the things that are classes. A class is a disease in this ontology. So I'm filtering where the predicate is type and the object is class, basically statements that determine that this thing is a class. So, and I collect the subjects. That gives me a list of all the class definitions in the ontology. So that's a first pass on the file that builds a collection containing all the class definitions. Actually, I keep only the URIs. I could, just as a simple example, if I run the first 100 and I return that, you will see the kind of collection that we're building, which is empty in the first 100. Let's give it 1,000 at least. There you go. So we're building a collection of URIs that are classes in my ontology, right? So if I keep going with that, what I'm going to do with that is, okay, I'm going to do a second pass. Let me go full screen. I'm going to do a second pass on the file, and it's not ideal from the point of view of performance, having to read the file twice. But because we don't have a query interface, that's of course you could download it, manipulate it, but we want to simplify what we're doing here. So what I'm doing is doing a second pass, and this time I'm saying, okay, I want to keep all the statements that have a subject, the classes that I have identified before. And I have them in a collection. So I'm saying just keep the ones that are in the list of classes that I identified before. In other words, throw away all the things that are not about class definitions.
Okay.
And I keep only the predicates that specify the type, that specify the label, which is the thing that I wanted, the subclass of relationships, the taxonomy, which is what I'm after, and also the cross-reference. And the cross-references are defined like that. Has DB cross-ref. That's the predicate that they use in the disease ontology. And in particular, I want the ones that start with mesh because they link to mesh. It links to other taxonomies that we're not working with here, so I just keep those ones. And with this, I'm just building a URL, an RDF document, let's say. I can show you briefly what that's doing before I call the final input. So if I run that, and I've made no mistakes, so it's doing a first pass, collecting a bunch of all the classes that are defined, and in the second pass, is getting for these classes all the relevant predicates, right? And you get things like, this is a class, this is a subclass of these other things. So exactly the kind of taxonomical relationship. Mm-hmm. We also have the labels, so that's the name of the disease in question, and this is the cross-reference. So we have a reference to mesh. So it's kind of a way of subsetting. It's kind of running a query without having Sparkle access, right? So that was the objective. So that's what it's doing. It's keeping a subset of the triples, and what I do is after having run this subset, I finally call the input, like in the previous cases, and that final step is calling the input as RDF, and we will have the taxonomy built. Now, if I load it like that, what's going to happen? And that's something that I wouldn't like to happen. I would get things typed as class, and subclass of would not be aligned with my terminology. I've called it has parent here, and I've called thing mesh diseases. So one thing I can do, and it's featured in Neosemantics, is I can define mappings, and I can define aliases on how I want things named in my graph. So very quickly, I'm going to define two mappings, and I'm going to say, whenever you find a subclass of, the way I like to call it in my store in Neo4j is has parent. So use has parent instead of subclass of. And anything that's defined as a class in this ontology, I actually want to call it, I don't know, we've called this mesh disease, WD disease. We'll call this disease ontology disease, DO disease, or something like that, right? So that's what my mappings are going to be. So let me define those mappings. That's a quick couple of steps. Again, I'm going a bit quick on this one, but this is all going to be in GitHub. So I define first the namespace where I'm going to define the mapping. So one is in subclass of, which is RDF schema. And I'm saying when you find subclass of, call it has parent. That's the mapping. And the other one is on OWL. Whenever you find a class, call it DO disease. So these are my mappings, just two of them. The rest stay as they are. So if I run these mappings, and then I go ahead and finally execute the longer input. So that's the one that I had before. This time it's going to build the taxonomy exactly in the same style as the others, but kind of working around the fact that we don't have a way of querying it. And you may or may not want, if you have skills in RDF4j or in Jena or in RDF-lib, in Python, whatever your programming language is, you might want to load the ontology, parse it, trim it, and do it yourself. But this is a way, and I thought it was worth spending the time to show some of the options that offers Neosemantics to do this kind of thing.
Yeah.
So there you go. So in this case, it's a bit larger one, so 46,000. So it's going to be much bigger than the others. But now we have the three ontologies side by side. There's a final step of post-processing that we need to do, because if you remember the disease ontology, here we go. So I'm going to show some examples, and I'm going to put them in maybe in green. So we have the taxonomy, just like the others. I can zoom in, but you will see that in some cases we have the cross-reference as a property, and that's not the way I used to store it, right? When we have a cross-reference, and again, it comes from the fact that I couldn't transform everything in the ingestion process. So in this case, it was not just an aliasing. I want to transform that into a same as relationship, remember?
Yep.
So we have a cross-reference like this one. I want to say, okay, go find this mesh thing, which is probably already there. If it's not, I don't care because it's something else, but go find it and create a same as relationship. And that's exactly what my this fragment does. Let me copy paste it here. So I will basically explore my disease ontology diseases where there is a cross-reference. Not all of them will have. So when that is not null, what I'm going to do is I'm going to merge, actually going to do match, because there should be already an existing mesh entity. And the URI is using the prefix, the mesh prefix, but I get the actual name from the from substringing this code here. So I'm basically building on the fly this URI. If there's a resource that already exists, then what I do is I merge them together, I link them together through a
create
same
a new relationship. Yeah.
And at the same time, I remove my
the property
version of it. I mean, there's no point in keeping the two. So if I run that and I've made no mistakes, that should link 500 of them. Excellent. So now we should have the three taxonomies aligned together. And now we're in a position to run the kind of the pattern detection that I was talking about. I mean, it was a kind of a longer process to construct, but I think it was important to understand how we did it. So right, so let's do first a pairwise comparison. And one of the things that I want to detect, let me show it in the slides, is one pattern, here we go, which is different levels of granularity. Let me show what I mean by that. So sometimes in a taxonomy, you have a good alignment, but at some point you see that one of them has more steps than the other. It's similar to what we saw before, right? So this is more granular in this particular step, whereas this one only has one. How do I express that? Well, I can create a cipher pattern that actually shows that. Let me put it on the screen, because I think this one in particular is complex pattern, but relatively easy to describe. So first of all, I find a match between the disease ontology. I'm doing it between disease ontology and mesh ontology. We could do it with the other one, or taxonomies, right? So I start by saying there is a link at the top, right? And this is this link here. Right? So there is a link between the disease ontology and the mesh disease. There's a link at the bottom, right? And this link across taxonomies is based on a same as, right? So there's another one at the bottom, and between them, right, between on the disease ontology side, there will be a has parent chain.
Okay? Of course, yes.
So there will be a chain on this side, and similarly, there will be another chain on the other side. That's the other chain. Now, the condition for that to be misaligned is that the length of those chains has to be different. So if these two chains are different in length, then we found one of these cases. So it's a relatively complex pattern, but it's relatively also easy to express. So if I run this query, actually, let me simplify it to one first, and then we'll extend to more. Here we go. So let's use the same as on one side. Simple.
Here we see one is missing on the
so we have a
ontology.
Intermediate one in the mesh disease that doesn't exist on the disease ontology. So that's a great pattern. I mean, and it happens more often than we think, right? So different levels of granularity. So question, I mean, do we want to extend this? I mean, there is a reason for that. And again, let's put this in context. Here, I'm doing just an exercise. But in your case, you might want to, if you have two product classifications, if you want two departments looking at data from different angles, you will want to make sense of that. Maybe you want to extend that. Maybe you want to get rid of this one. Maybe that's redundant. So how do you make sense of it? How do you, or maybe keep the two, but understand that there's this additional level of granularity? That's something that you can easily deal with. And yeah, like we showed before, we can do that at scale. I mean, maybe visually in some cases it's going to be easier than others, but sometimes it can be a bit messy. But if you look at them individually, it's maybe the visual is not so important. The important is that we can capture them and then act on them. That's one example. And like I was saying before, we can do exactly the same pattern, but this time, instead of between the disease ontology and the mesh ontology, we can do the same thing between disease. No, that's the one that we did before, right?
That's the one we did just now.
Yeah, we could change the. I'm going to move to a. I mean, it seems obvious, right, that you can change the type here. If I, instead of doing this between mesh and DO, I use the Wikidata, I would get the same type of situation between Wikidata, right? So
yeah,
I don't know. I don't know if that's going to return a match. There you go. So that would be the same, but this time between Wikidata, and that's probably another more.
Yeah, now here we see Wikidata is a little bit less.
That's not what I wanted to do. I wanted to show this.
Clear.
So there you go. So this is the Wikidata. It's much simpler than the mesh, which has loads of. I'll show these again. There you go. Another case of this, right? So if we want to explore it visually or if we want to act on it, up to us. Good. There's another pattern here. I'm going to show that I call generalization. I'm going to go a bit faster here because I'm conscious of time, but here. But what's happening in this case? So we have two disease ontologies, right? That actually match to the same.
Okay.
The same one on the mesh side.
Yeah.
So these might be a generalization. I mean, does it mean that these two are synonyms? Is there any relationship between them? In this case, there's not, right? So, well, they seem to have a common parent. So there's some kind of relationship between them. Let's ignore this one for now. But you see what I mean here, right? So, let's make it so big. But they are related in a way, but in theory, they shouldn't be identical. Or maybe they are, but that's the thing, or similar, or they align. Yeah. They kind of generalize to the same concept on the other side, right? So there you go. That's another pattern that we can identify. Although probably, and just to conclude, the most interesting one, well, I guess the immediate that you would look at is, because this was pairwise comparison, taking two of them. But if we want to look at the three of them, sometimes we will want to find these perfect triangles that I was referring to at the beginning, right? So when we align, a perfect case where you have the same concept existing on the three ontologies, that should form a triangle. And that's exactly what we can detect with something like this. Look at the triangle is easy to describe because, we start with the disease ontology, same as Wikidata disease ontology disease, mesh, and all the way back to the Wikidata, which is this one. So this kind of forms the three sides of a triangle. Now, I add additionally, for it to be a perfect triangle, because we see that sometimes we have multiple same as, right? So that would be aligned, but not perfect, because there's an element of ambiguity here. So which one does this align with? This one, or both? So what I'm adding here in the where is that I want the number of same as connections coming out of each one of the elements in the triangle to be the two that form the triangle and not more than two, exactly two. So that's what I'm saying. So the size of the number of paths of type same as that this is showing, both for the Wikidata, the disease ontology, and the mesh disease, it's always two. And I can run this query. I don't know if that was clear or I went too fast on it, but these are the perfect triangles, things that exist on all three ontologies, all three taxonomies.
Yeah. Right. From each node, basically you check that for each node you have two relationships.
Exactly. So what I'm saying is, first they form a triangle, but out of each one, out of the Wikidata, out of the disease, and out of the other one, there's only two same as coming out of them. So there's only the two legs. Because if there were more, yes, there would be a triangle, but there was still ambiguity. and I don't want that. So this is what I'm making sure here, and all these should verify that. I mean, they're kind of riding on top of each other, but they're separate triangles ideally. Here we go. This is this being trying to be helpful and connecting the nodes which I don't want to happen. So it should be perfect triangles. So this is just the browser trying to be helpful, but these are all triangles. Okay, so these are perfectly aligned concepts. And then one consequence of that, and I finish with that, is that when we have 3 sides to it, if I'm missing one, I can predict it. I mean, it's not really a prediction. It's kind of an easy one. If A is equal to B and B is equal to C, well, I know that A is equal to C, whether you tell me or not. So would it be a way of enriching and completing taxonomies? That could be a good use. So in this case, what I'm saying is, with a small variant of that triangle-based query, what I can do is, okay, let's find an incomplete triangle. Let's see what's happening here. So I have the Wikidata disease connected to the disease ontology, and disease ontology connected to the mesh. But there is no connection between the mesh and the Wikidata. So that's the missing leg. So when that's not there, and the others still verify the condition that there's non-ambiguous that we did before. So if that's the case, then I can anticipate the other leg, and I can provide in the form of triples, hey, we could complete the Wikidata by saying, I know that this resource has as disease, the D was the missing disease ontology, right?
Mm-hmm.
So I could produce a number of triples that I could send to, I mean, I could actually contribute myself to Wikidata, right? I could just add them. So, and using the P486 that, as you remember, at the beginning, Alex, was the 486 was the mesh descriptor. Sorry, I was talking about the mesh, not the disease ontology. That's the mesh ID. So there you go. So I think I'm going to stop here because we've gone a bit over time. But I hope that gives an idea of how we can deal with multiple taxonomies. And once we've loaded them, which took us a bit longer than planned, we can start running pattern-based queries with Cypher to uncover unexpected or expected, but hard to find patterns of misalignment. So that's it.
Yeah, cool, very interesting. And then what you just said is I think is then the next step that leads to either you complete your data and what you said earlier is you have different teams maybe working on different things, and you want to ideally find, is there a gap in my data? Is there ambiguity? Do we have the same description or the same word or the same thing for two different teams talk about it differently, or is it something else? And then you connect it in and then find, okay, actually this is redundant, this is indeed the same, or maybe actually yes, there are differences between these two we didn't account for previously.
Yeah, absolutely. So that's I thought that could be, I mean, I could contribute. I mean, the thing is that would break my example, but I could, because how you can contribute to Wikidata. So I could come here and say, hey, go and get this entity here, and we can actually, I can open a new tab. So I could come here and say I could add predicate P486 with these values. So I could come here and add the mesh identifier, which doesn't seem to be there. There you go. So you have all the rest, GNN, National Library, but you don't have the mesh one.
Yeah.
There you go. So that would be a good way of completing the session. So
yeah. and
there you go.
And yeah, I mean that's very interesting. We had a couple of questions, so maybe we quickly look at those, particularly, and I think this is maybe more of an understanding question than anything else, is when we have the graph and once you see that, how was the model defined, or how did the model come to be?
Well, in this case, it was a relatively simple model because there was only disease and subclass of, or in our case, has parent, or So it was a relatively simple model exercise. So we just focus on the taxonomical, classification plus the same as across taxonomy. So not much of a modeling in this case, and
I think with using neo-semantics and loading from RDF, the model, it's not as much as a modeling. Well, there's some modeling we have to do or we have to think about, but more or less it comes already with
exactly, it comes as a
data.
graph. So So when you query Wikidata and you're basically selecting a portion of the Wikidata graph, it's already a graph. So you are unless you want to transform it on the way, which wouldn't make a lot of sense in this case because it's already a graph. We're kind of skipping the modeling step and just loading it as is.
Yeah. And the other one, I guess, more was like on the visual aspect is we looked at the graphs and we looked at the nodes and the relationships. But is there? You can obviously look at it in a table view. You can select just in browser you want to output it as a table and see it there. And like we said before, in some of these cases it might be even easier to understand what's going on in some cases when you see, okay, there's is with the nodes it could be a little bit confusing, but then you visualize it as a table or render it as a table, and it's perfectly
exactly. So you could,
doable.
there's all sorts of analysis that you can run. You could produce a table with the list of nodes that you're interested in with the degrees, or with the, you could even produce a table where, for this particular disease, is there a match on the taxonomy B and taxonomy C? You put it green or red or something. There's plenty of representations that are not necessarily graphy that can, can be useful in some cases, but can be sometimes more complicated. But yes, how to present it is, however, is useful for the consumers in this case. And tabular is definitely a valid approach. Yeah,
absolutely. Yeah. All right. I think that brings us around to the end of episode number 14. Again, thank you very much, Jesus, for presenting and for showcasing this interesting application of neo-semantics in combination with various sources on Wikidata. What was it? Mesh and
the
disease ontology. So very cool, very interesting. I hope you enjoyed it as well. If you did, like or subscribe the YouTube video if you can. That would be super helpful for us to see for more episodes in the future. And with that, I think we're out. Next live stream is taking place this week on Friday, I think, where our colleague, no, tomorrow. Well, what I'm saying, tomorrow, obviously, 8th of March, International Women's Day. So join us tomorrow when we talk about women in tech at Neo4j and beyond. And with that, I wish you all a great day. Again, Jesus, thank you very much, and see you soon.
Thank you, Alex. See you soon.
Thank you. Take care. Bye.